Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD scholar IIT Palakkad. Today we will discuss week 11 of the live discussion section. In this we will discuss lecture 51 to lecture 55 by Professor Ashok Desai IIT Kanpur of the subject Turbulent Combustion Theory and Modeling by NPTEL. This is the week 11 of the live discussion section. In these sections, the problems are taken from the book HR Turn, An Introduction to Combustion Concept and Application, 3rd edition. Let's start our first problem. Estimate the turbulence intensity Vrms and the relative intensity Vrms. The turbulence intensity Vrms prime and the relative intensity Vrms by V bar for the experiment described in example 12.1. Okay, what is the example 12.1? I'll all things I will go through now. Okay. What are the things given? This is the first problem. So example 12.1 I will go through. We need to find some of the assumptions we can make. Wrinkled laminar flame region. Then time collars model applies. By using Dam collars model, so from example 12.1 we will know that St equal to 8 meter per second and V bar is your what 6 meter per second. Okay. So now we have to find out Vrms prime from the above relation. Okay, especially from equation number 1. So VR prime is equal by 0.5 divided by 0.5 minus 1. Okay. There is no SL, so the answer comes out 7.5 meter per second. Sorry, actually forgot 5. There is SL 0.5. Okay, so the value comes out to be what? 7.5 meter per second. So VRMS prime equal to 7.5 meter per second. So what is VRMS prime by V equal to V bar 7.5 by 60, 0.11. Okay. Equal to 0.11. Let's go to the next question. So that the equation 12.8b follows from 12.8a for VRMS prime divided by SL is very less than 1. What is 12.8a? I will write down now. So the Kevin and James correlation the wrinkled minor flamelet region is your equation 12.8a. What we need to show? Equation 12.8 reduces to equation 12.8b for BRMS by SL very less than 1, whereas BRMS prime by SL very less than. Okay, so first we see what is equation 12.8a. The kind of binomial series expansion of 12.8a. ST by SL. And multiply with 0.5. In the higher order terms, to the power 4 can be neglected. That we see now later on. Now we see one condition here given, VRMS by SL very less than 1. Condition now we have to apply. Means VRMS prime by SL very less than 1. VRMS prime by SL to the power 4 is also very less than VRMS prime by SL square. So that means we can final expression 2 plus 2C VRMS prime by square to the power 1 to again expand the rule of binomial. So ST plus 1 by 2 2C by SL square plus 1 by 8 4C VRMS prime by SL to the power 4th plus SL to the power 4 very less by, so this term we can neglect. ST by SL equal to 1 plus to get cancel BR prime by SL square. So expression is your turbulent and laminar flame speed. Okay, this formula you should remember. Directly the be there. Maybe they will team can be transition period also of turbulent. They can, so this is the transition flame. So that case also this formula can turbulent also they are okay. SL okay. Okay, so very important expression. Sure. Only for this condition this formula is applied. If nothing mentioned, just directly take this formula. This is as a default also. Mostly all the numerical and MCQ questions directly you can take. They are not mentioned. Now let's move to the next one. If ERMS prime is doubled in the calculation given an example, does the estimated combustion regime change? If so, in what way? All in the book. From the person asked in this exercise. So for that actually you should go through 12 example and book a certain whatever information I will pen 12.2. So what are the questions? Problem. Meta-Galchis correlation apply for cell laminar flame speed. The important thing in this type of when VRM double, triple, all these questions are asked, always directly use the meta for flame speed. what is Kohler's number? Time constant for flow, time constant for else involved in the combustion. Tau flow L naught by ln scale. All these data actually 12.2. All these data are actually directly take that not given BRMS and tau flow you can take power minus is obviously. So now put it, but question from the early time scale L 3.8 L 0. Pound 4.4 10 to the power minus doubling VRMS VBMS modified is equal into VRMS time equal to 10 because 10 is your VRMS prime meter per second. VR modified then per have tau flow and tau we have to put it 0.5 by 1044 to the power minus 3 30.1 which is then 100. So there is some condition for what flamelet AD. Okay, is I'm calling flamelet. The question is asked: does the estimated combustion regime change, or if so, not why? Okay, for a flamelet AD, if there is a flamelet AD, then by doubling anything you do, there is no effect. Is it really a flamelet AD or not? That's actually here. So if you see here, actually one condition for a flamelet AD is satisfied is your dam Kohler's number less than 100. It should be great. If it is greater than, then obviously it's having some first condition. Actually, there is actually 4 conditions. Let's see if there is 4 conditions or not. If one of them is not satisfied, that means it's not a flamelet AD. And if there is flamelet AD, that means doubling is having no effect. That's the whole thing. And we find out what Reynolds number. For Reynolds number, actually there is a condition for also flamelet. Reynolds number VRMS prime not by in 12.2 the fluid isooctane. directly if we compare, it's a 2 times of whatever the initial errors for the prime. Okay, so yeah, find out the 2 times. First you have to find out rho p equal to rho rt, direct ideal case equation you can find to rho rt, so rho equal to py. Pressure is actually 15, the one 15 atoms atmospheric. So we are converting to all things into SI units. All this data is actually given. Then your VRMS 10, del naught is 0.03 divided by your mu for the isoctane for the given pressure and condition 689 10 to the power minus 7. You see values comes out to be 2 111477 each. Double 2954. Actually also this is also in the range. Your Reynolds number 10 to the power, if it is in this range means template region. Second condition actually satisfied. Satisfied. Your lengths, find out some of the lengths. Not into REL to the power minus 3 by 0.03 2954 to the power minus 1.6 to the power minus 5 meter. What is I lambda L 0.112 A by not by lambda L delta L 0.03 by 3.9 into 10 to the power minus 5 is 769. Very high value. Okay, perfect. So basically 10 to the power minus 2 less than by lambda than 1 and 1 less by than 10 to the power 4. If in this range, obviously this is what third condition satisfied. This is 0.412 and this is 716. So if you see 1, 2, 3, 4 fired, but flame mean RMS prime. Question of flame related. So in can be asked in 1 mark question. Directly they will ask, okay, if doubling the BRMS prime, are the conditions 3 or 4. One option they will, one option they do condition. They ask you what is the effect of what BRMS prime, if or triple or what thing. You can directly tell no effect. That's what the person to consider the turbulent premixed combustion given in the following conditions. Propane air mixture is there, phi equivalence ratio, unbound temperature 350 Kelvin, pressure to atmospheric, mass prime 4 meter per second, length scale also given 5 mm. Calculate the characteristics, chemical and flow time, and determine the value of time color number. Are these conditions representative of fast or slow chemistry? The fast chemistry, slow chemistry, things we have to see. This is also similar question, very simple. So we should know at least actually what is the correct procedure for this. First, what are the things? 516 pressure to atmospheric, propane air, EU 300 Kelvin, S prime 4 meter per second, L naught 5 mm. To find chemical time scale, flow time scale, time colors number. One more thing, fast or slow. Some of the assumptions also we can. The propane air flame, we are assuming the flame temperature as 2000 Kelvin. The Med Galchis essence. Simple theory or cell, model and air properties. Yeah, the now solution. First we have to find out the laminar flame speed. Know previously how we should find out. For propane, some of the tables. Huh? 0.16 and 16 0.8 in 5 minus 1 and 8 0.6 minus 1 and 0.5 PV minus 0.5 minus 1 plus out 2 4. Yeah, formula L reference flame speed is Bm plus 5 minus Im substitute 4 minus 130.65. Actually this is a of the old work. Find out the flame speed. Okay, from the, again the from the flame speed find out all these things. Okay, then we find out what the how chemistry, how flow. From there we'll find out from the dam color, or obviously we can get to know the slow or fast. Obviously dam color, that's the reason to put the 0 point minus 1.08. From here find out the reference flame laminar flame speed 0.27 centimeter per second. The laminar flame speed formula, which is L is equal to SL reference by TF equal to the power gamma by P to the power beta to 1 minus to 1 in dilution. Obviously there is no, we are not assuming dilution. We have to just substitute values. convert it into SI units. Fifty by 298 by 1 plus 2.24. If you solve SL as 0.2 meter per second. Got the SL. Now we have to find out some of the basic constants like alpha. Alpha is your AT bar A by rho Cp obviously. So yeah, not that much straightforward. Find out T bar first. T bar is your 1 by 2 flow temperature plus 1 pound fuel temperature. Flow temperature we assume 2000 Kelvin. 1 pound is you all know 350 Kelvin. 1175 bar. For that T bar find out A and Cp. Those things directly we put it 75.1 into 10 to the power minus 3 divided by rho u. How you find out rho u? Rho is equal to P into molecular weight divided by Ru into Tu is 2 2 into 101.325 into 28.85 is your molecular weight of the what? Air divided by 8.35 into 101 well temperature 350 Kelvin. So we will find out the unburned gas temperature. The unburned gas density as 2.01 kg per meter cube. Rho u will get rho u 2.01 and Cp 1171. Okay. So these are taken from table C.1 at the rate 1175 Kelvin. Okay. Now you can find out what is alpha. If you solve it, we will get alpha as 31.92 into 10 to the power minus 6 meter square per second. So alpha, which is the important thing for finding delta L. Your delta L 2 into 31 to the power minus divided by L, which is L also value you know 0.034. So delta L equal to 1.878 10 to the power minus 3 meter outflow not by VRMS prime AP into 10 to the power minus 10. VRMS also 4 meter per second. And the outflow, if you out, 1.25 10 to the power all the hard work is for time scale. So see how come to delta L by SL 1.878 10 to the power minus 3 by 1034 point 0.0556. Time scale flow time can now find out the first number which is flow by tau 1.25 by 55 to the power minus 3 power minus. Yes, obviously it should be less than 1.273 which is less than 1. All number less than 1 means we have one very good condition. So here what 10 to the power minus 4 less than Damkohler's number than 1. Then distributed reaction. These are very important conditions. They can directly ask you on this question. Okay, if they will give you the range and they'll tell what is the condition. To the power minus 3 less than Damkohler number less than 100. Or yet we already see. So both these conditions are comes under one category. Flow chemistry. So if that means also if your Damkohler number is greater than 1 means it's a what fast chemistry. 99.9% of the papers works fast chemistry. It's very easy to model. Damkohler's number greater than 1, but for the accuracy cannot recent works cannot rely only on, and also go for some flow chemistry cases. Okay, especially when you have a tracking of ADs. Okay, there is a very useful of ADs, especially for turbulent flow, not the laminar. Wrinkled or M sprinkled laminar flame. Laminar one, we will apply turbulent. First chemistry means turbulent flow is the best thing. First chemistry interaction is so not that much accurate to go for, but slow chemistry reactions. Okay. So for this question, good one is just slow chemistry interactions. As fast chemistry, very easy to simulate and very reliable as compared. So, this is also a turbulent methane air flame is stabilized in the wake of a circular rod of 6.4 mm held perpendicular to the flow. For inlet condition of 1 atmospheric and 298 Kelvin, the blowout velocity is 61 meter per second when the equivalence ratio is unity. Okay, that means the stoichiometric condition. The recirculation zone behind the rod is 6 diameter long. Estimate the turbulent thermal conductivity alpha T. How does the value compare with the molecular thermal diffusivity alpha? Use air properties of alpha. Circulation zone, all these things are there means there may be a chances of what? Blowout. Okay. Where is the recirculation zone behind the rod is this. So all this means you should think of blowout model for blowout. All these things we have, that condition we will apply. When there is a storm, recirculation zone, all these things are mentioned. Also, if you see, they directly, also this is easy because they directly mention the blowout velocity. Mention that, then it will be very tricky. Maybe you can expect they don't mention. Now you can also get to know condition for blowout. So given 6.4 mm, that condition pressure is equal to 180 atmospheric, temperature between blowout velocity also given, let it be b naught is equal to 61 meter. So now we have to out what? Find alpha t and compare with alpha equal diffusivity of what? Air. The assumptions we can make. First assumption for blowout is Splading's model. Let's start the solution. What is V naught? 2 into rho naught L SL by 2 alpha T square. Is alpha T L by rho to rho naught L by V naught. The two things given. These two formulas we can apply. So first we will find out 298 Kelvin at m. Naught is equal to P into molecular weight divided by RU into T. 101.325 0.85 0.315 the 291.18 G per meter cube. Rho naught we have. Now adiabatic condition 2200 Kelvin. Pressure we are assuming 2200 rho 0.16 per meter cube. L to 6 times of that. 6 into 6.4 into 10 to the power 3 equal to 0.0384 meter. L 2 plus 3.71 power minus 4 temperature square. Normal atmospheric temperature. One more formula for your laminar flame speed. If you solve it, you will get flame speed as 0.43 meter per second. So now you have to find out what alpha T. Alpha T is equal to L by rho 2 into rho naught L by V naught 0.43 by 0.16 2 into 1.18 0.03 by forward speed 61 meter per second is equal to 40 means what for the 2200 case. Okay, at the flow when there will be flow blowout, not obviously it's not at the atmospheric condition, no, obviously at the high condition only this blowout, the chances are there. Okay, and that blowout condition we are finding the thermal diffusivity. That's the only difference in this question. Instead of normal condition we are finding the properties for the blowout conditions. Okay, it's the only thing difference in this question. So now we have alpha t, so we can compare which is very what greater than your alpha, which is 714 into 10 to the power minus 6 meter square per second, alpha t of what air. What your methane air. Okay, that means you can understand that there will be too much thermal diffusion in place of what, if there will be methane or a fuel is there, there will be very higher thermal diffusivity in the flow blowout condition as compared to your if there is only. Okay, that's the only takeaway from this question. Just go, because all these questions are important, I just first go through questions, take away whatever things and how these things. Actually I forgot to tell what type of question they ask you. Okay, since they can ask you VRMS, obviously VRMS prime, they are not going to ask you VRMS prime directly, and ask you what is this relation. Relation is important, relation you should remember. Okay, the derivation, all this ask. Only one thing in question is important, and from this we can obviously know how to find out VRMS prime. Then yeah, one condition, and for this question, what is the assumptions we are making? Wrinkled laminar flame region. Okay, wrinkled laminar flame region we are assuming. Okay, why I am actually doing this? Because if you can correlate all these things. What is the wrinkled laminar flame region? There, when Damcolor's number is greater than 1, then only we are assuming that what, wrinkled laminar flame region and your fast chemistry. So here we are assuming wrinkled laminar flame. Okay, and then we are assuming 0.5 meter per second. So that means we are, what we are assuming, we are telling, okay, so actually what, most of the problems, if nothing is mentioned, we are only taking directly a laminar flame region. Okay, so that the calculation will be very what, simple. The region laminar flame region, and when there will be V bar, this is, you see also V high, 68 meter per second. Okay, very high, then only will take Damcolor's number, because the history is very fast, the flow is very fast. Okay, region for this wrinkled flame region. Why I am now going through all these things, so that you can relate and you can correlate why we are doing all these things, because this is 11 is somewhat, if you know the correlation, it will be very useful for you. Next question, if you see, Kelvin and Williams correlation are applying for what? Wrinkled lamellar region. That means you can see one question they can ask for the wrinkled laminar lamellar region, which correlation applied? 3 or 4 options they, okay. One of the option will be what? Kelvin and Williams. Okay. This kind of okay. Now next question they can ask. Okay, and wrinkled laminar flame region, which is the basic assumptions you can okay. For this is the basic assumption. Mostly we are taking RMS prime by SL less than. Also one question they can ask. Okay, 2, 3, 4, 3, 4 questions. But questions we can also from this. Okay, this derivation obviously they don't ask you, but they can ask you this correlation is very important. ST by SL equal to 1 plus C into BRMS prime by SL square. Okay, whole square. Are very common. Next, for this condition, this formula applied. Then, when there will be what? Net health correlation. The when the correlation we are applying, when you check, okay, BRMS prime having any effect or not on the combustion regime. Okay, for that case only we are applying net health is correlation, and that's for the whole thing. And to check for VRM, net health is correlations we are applying. And from this there are some of the formulas like Ramkolas number. Okay, basic question they can ask that what is Ramkolas number? It is tau flow by tau chemical. What is tau flow? Not by BRMS. Okay, BRMS prime. Okay, then what is tau chemical? Delta L by SL. Some basic things they can directly ask you questions on this. They will not prime, and then they ask you what is tau flow, and then again delta L SL given. Okay, man. Obviously from this ask you what is Ramkolas number. Also can questions can be asked as your MCQ. Then yeah, so these are the 4 conditions. You should also remember what are the 4 conditions for the flamelet regime. Okay, first one is your Ramkolas number less than 100. Then your 10 to the power 4 to 10 to the power 8 is the range of your Reynolds number. Then del K by delta L should be in between less than 1. Okay, 10 to the power minus 2 to less than 1. And L naught by delta L will be less than 10 to the power 4. 1 to less 10 to the power 4 is the range. This is the from 4 condition, basic condition for the flamelet ID. Next. This is also same question, tau chemical, tau flow and Ramkolas number we apply, and we are checking it fast or slow. Okay, but for this first we have to find out the Metcalfe correlation, and we have to find out the SL. So SL, how we find out this? Already we see in previous chapters, previous lectures. Find out the SL, then from this SL and substitute to find out what, because why this, what is the importance of SL? Because delta L by SL, that is your what, tau chemical. From there from the, because in here actually we need the what, for that only we are what finding by using Metcalfe code. Here are some of the 3 conditions. Then one means this does not mean that there will be only one condition. Okay, so to see the range, okay, 10 to the power minus 4 to dump reaction, and flamelet ID is 10 to the minus 2 less than 100. Okay. And these are all for slow. For the fast, it's the blowout condition. Okay, the blow velocity circulation behind the rod is this. So then we have to, here what is the difference we done here? For the, we are applying the what, spreadings model for the blowout. So for the blowout conditions, for which kind of model are applied? Okay, 3 or 4 options they'll, okay, from there you have to choose the spreadings. Okay, the spreadings model, these 2 equations are very good. Remember what is alpha t, what because directly this formula will be asked as a question. They will put one cube root here, they will put one two or cube here or fourth power here. Okay, ask you the question because this formula also important. In the procedure of finding is absolutely same. Okay, only the difference is here we are finding in T adiabatic. Okay, previously we are finding in the atmospheric or T bar, especially T bar we are finding here in place of T bar where we are finding at the what adiabatic condition, because it's the blowout. For blowout we are finding at the adiabatic condition. Okay, if there is a normal conditions, they ask you find out laminar flames, column number, all this. Directly just use the what T bar. From this T bar find out like this, T bar equal to 1 by 2 TF by, then find out alpha based on K. Remember K and CP only based on T bar. Rho U you find out based on what, your TU. Rho based on T and K and CP based on T bar. Okay, then yes, and also if there will be a chemical reactions are occurring. Okay, you can see the thermal diffusivity for the fuel air mixture is very high as compared to your what only if there is only air. That means to handle the thermal diffusion condition also in the, that is the reason why means for the assuming what it's a fast chemistry model. Okay, if there is a blowout condition are there. Okay, for example, if a blowout flame blowout, assuming as a fast chemistry model, actually very difficult to predict. Okay, most of the case nowadays the fast chemistry predict the blowout condition, actually a quasi condition, special chemical best to solve tackle all this kind of for the whole. Maybe next lecture there will be one summary section, 12th lecture, and there will be one summary section. This we can end the section. If you have any doubt, ask doubt. Ramesh, you can ask.
Sir, actually, this lecture 51 to 55, most of the turbulent chemistry modeling was covered, no? The related to probability distributed function kind of things. So, any questions we can expect from that, and one or two model can we try in the next session?
Is this person's I think included or anything else you are asking?
Yeah. No, I was generally asking because 51 to 55 lectures, if you see, most of the turbulent chemistry models professor have discussed.
Ah, okay.
With related to that, any this because understanding that, but that
Yeah.
essence is very difficult. So that's what I asked.
Yeah. That's the only reason why actually I told you all these things. How these things how these different thing you see have don't have. Okay,
Problems. Okay.
that's the whole theoretical. Okay,
Ah,
mostly
ah,
theoretical
okay. Okay. Okay.
for problems is these kind of goes.
Understood. Okay. Okay.
Thank you. And I'll also if you have any lectures related. Smith, have an